Hi, welcome to your lesson on functions. We've talked about functions, specifically composition and inverses already. This video is going to take you a little deeper into both of these topics. Let's get started. So let's recap what composition of functions is. Let's say you're given one function, f of x equals 2x plus 1, and another one, g of x equals x squared minus 2. If we said, let's compose those two. That means one of the functions is inputted into the other. In this case, we have f of g of x. That means the g of x function, this one here, must go into the f of x function. What that gives us is this. Notice we have written the f of x function to x plus 1, but the x has been replaced by the g of x function. So this here has been inputted into this x, and we have this. That's basic composition. Now let's take that backwards. Let's decompose functions. So let's say we had one that is composed and we want to break it apart into its original two. So here we have h of x is f of g of x. So some function h of x was made by doing composition of f and g of x. And we know that that composed function is this. Now, if you were told that f of x began as x squared, then what is g of x? So think of it this way. You have the composition here. You know the original is this. What needed to be inserted into this to turn it into this? I hope that one you're thinking, okay, here's my f of x function. Therefore, g of x must be this. Because now if I put this g of x function into this one, I get that, which is what we had here. So just pause if you need to. It's really important that you can kind of unwrap functions like this into their components. So here's f of x, g of x. We have decomposed this one. Let's try this with a few more. So that's what we just looked at. Now here's four more. Take a look at A and B. Can you find out what your f of x and g of x functions would be there? If you decompose this one into two functions, what would it be? And likewise this one. Okay, let's see if you figure that out. In the first one, I have g of x is this, f of x is this. So we had some f of x function, and into it we put this function. And notice we have this, right? So if x minus 5 was inputted into this x, we would end up with this. So now you can clearly see two functions. In B, same thing. I can see this a plus 2 repeating here. So I'm thinking maybe that was inserted into an original function. And here's what we have. Here's our original function, a squared minus 3a. And now each of those a's had this function inputted in right here. So that a plus 2 went in here, and that a plus 2 went in here also. And we end up with that. Okay, so I hope after 3 examples now you're getting the hang of it. So let's try C and D. Okay, in C, here's our f of x function, 1 over x. And their g of x. So now this is inputted into this x to give us this one here. And likewise in the last one, we can see this here inside the parentheses. So maybe that began as just 4x, and there's 4x here. And then we have this other function, x minus 4 is inputted into there. Okay, so again, I hope you're getting the hang of decomposition of functions. Now let's apply this in a real setting in a word problem. Let's take a look at what we have. Oh, sorry, I forgot. I have one more here for you. How about this one? And it says decompose fully. Now I want you to think of this one not just as two parts, but maybe this is made of 3 functions. So challenge yourself to write the 3 functions that were composed to create this. Okay, here they are. We have, let's begin at J. We have this function, root of x, right? We can see the roots. So kind of the outer part of this one is a basic form would be root of x. Into that, we insert an x to the 4th power. So imagine that went in here, input. But then into the x to the 4th power, we have x minus 2. So that was inputted into there. You can see now how clearly how those 3 pieces come together to make this. Okay, so here's the word problem. We have an insurance company, and they offer insurance rates based on age. In other words, the older you get, the more insurance you'll have to pay per month. This is going to be per month here. So the formula for calculating a person's monthly insurance premium is this, where n is the year a person is born. So in this case, I want you to do A, decompose this formula. into two component functions, f of n and g of n. So can you decompose this? Let's try. So here we go. I saw it as we have one function, that's 2017 minus n, this one here, which was inputted into this one, right? If we have the basic function 1.25 n, and then this one replaces this n, it's composed with that one. So we can see the two functions that make it up. So now what do these functions represent? That's the next step. And B, explain what each of these means in terms of this insurance policy. And remember, n represents a year of birth. So what does the f of n function represent? Well, f of n is calculates the person's age, right? If n is somebody's year of birth, then this is a function that gives somebody's age. And then g of n, well, that's the function that tells you what monthly insurance rate they will pay, because it'll be 1.25 times whatever this function produces. Okay, so n being their age here. Okay, so there's a decomposition and description of those two functions. Now let's look at C. How old is someone in 2017 if they're born in 1968? Which of our two component functions would you use for that? Well, to solve that, obviously we'll use f of n, because that's the one that gives age, right? So the input is 1968, so I put 1968 here, and that allows me to calculate their age of 49. Now, how much will their monthly insurance premium be? Which of the two component functions should I use for that? In this case, I will input their age in here into the g function. All right, so 49 goes into the g function, put it here, and we get their monthly insurance premium. Of course, you might be thinking, I could have just used my initial formula, right? That's the whole point. That I could have put the year of birth in here, and then it would automatically solve both of these steps in one step for me. But this exercise is more about understanding how these components work and how you can have one function producing something very specific and another one, and when you compose them, it gives you this new end result. So that's what this is all about. Okay, so let's try D. Manuel pays this amount per month. In what year was he born? So in this case, you can, again, you go through both of our component functions, working your way backwards, or in this case, I did go back to the original. I put in 41.25 for C of n, which is our monthly premium, and solved it backwards to find out he was born in 1984. Okay, let's keep going. And now we're going to switch from composition of functions back to inverse functions. And inverse functions, we do use composition while talking about inverses often. So let's take a look here. Here's a function. I can rewrite that instead of f of x as y, because often when we're finding the inverse of a function, it's easier to see our y and our x clearly here. Because when we create an inverse, we swap the domain and the range. So we're going to swap the x and y values here. All right, the domain and range are interchanged. Now we go ahead and rearrange this for y, because we usually present functions as y is a function of x. So solving this one, I subtracted 3 and then divided by 2. I have this. And for inverses, we can use this notation. So now we have our original function here and the inverse of it here. The interesting thing on a graph of an inverse is this. So here is our 2x plus 3 function, our original one, graphed. And then here is the x minus 3 over 2 one, the inverse. Inverses will always be reflections over the line y equals x. That is just what happens when you exchange the x and y values, the domain and range. For example, we have a 0.13 here, and that will be 3,1 on the inverse right here. The x and y values are changed. Okay, great. So that's a recap of inverses. Now let's take inverses a little bit further. Over here, we're going to do a little investigation. We have three functions, f of x equals x, f of x equals 1 over x, and g of x equals 3 minus x. Those three functions are graphed here. Now, your job is to draw the inverse of each. And remember, when you're drawing the inverse, you can begin with the line y equals x, right? Just as we had here. Oh, let's go back. Just as we had here, you can draw that line in, and then pick several points and swap their x and y values and plot them to create the inverse. So try that for each of these three and see what happens. Okay, so what did you notice when you tried that? Well, I hope you noticed this. Okay, I drew the line y equals x here, And actually, my original function here is y equals x. It sits right on that line of symmetry. So if you were to invert that one, it wouldn't go anywhere. There's no mirror image because it's right on the line, which is the mirror. So it would remain the same. So the inverse of that one would be the same line. Okay. Now over here, draw my line y equals x. And now if you went point by point and reflected them, for example, this point, where would it reflect? Well, it would reflect over here. Oh, interesting. So in this one, if you did the mirror image reflection, you would end up reflecting all these points right on top of these. So again, the inverse of this given graph is itself. It would flip over that line and just land on itself again. How about this one here? Well, if you draw the line y equals x, and now you can notice that the line I was given is actually perpendicular to y equals x. And if it's perpendicular to it, and again, you did a mirror image, you flipped this red line across the mirror, since it's perpendicular, it will just flip onto itself on both sides. So in all three cases, the inverse is the same as the original. And that happens sometimes. It's rare, but those are called self-inverses. So all of these are called self-inverse functions, which means they are inverses of themselves. I want you to write a definition of self-inverse function. That might be tough to do, but what do you think? Try it out. Okay, here's a definition. A self-inverse is any function where f of x equals the inverse of x, okay? And well, that's what we said in words, that these would invert and become themselves. So algebraically, we can say the original function is equal to its inverse, okay? Now, write an algebraic definition similar to the algebraic definition for regular inverses. In regular inverses, we learned that if you put one function into another, either way, so g of x into f of x or f of x into g of x, and you simplify that, you would end up with x. That's what happened with regular inverse functions. If you put one in the other, you always end up with the result x. Now, could you write a similar algebraic rule for self-inverses? Well, that rule is identical, right? But in this case, instead of f of x and g of x, we say f and its inverse, because self-inverses, when you put an inverse into itself, or the opposite way, itself into the inverse, then you'll get x. So it's the same rule as for regular inverses, but now we're putting the inverse into its own self, or backwards. So a little bit strange when you see all this notation, but I hope you're starting to piece these things together. This, by the way, can also be simplified a little bit further. Since for self-inverses, we know that f of x is equal to its inverse, rather than writing put the inverse in here, we can just say put the function into itself. So with self-inverses, and let's remember this, when you put the function into itself, you will get the result x. And that is the big key rule for self-inverses. And notice it is very similar to the rule for regular inverses. So put a function into itself, the result is x. Okay, so let's use that property to try some things out. But first, we're going to do another graphical approach. Show graphically that f of x equals negative x is a self-inverse. So if you were to graph this, can you show that it's a self-inverse? So here's a coordinate plane. What would this look like? This function here is basically y equals negative x, right? How would you graph that? Well, y equals negative x looks like this. It has no value after the x here, so this could be written as plus 0. That means the y-intercept is 0. And we have a negative here, which implies a slope of negative 1 over 1. So y-intercept of 0, and then down 1 over 1, down 1 over 1. This is the line y equals negative x. Why is that a self-inverse? Well, if we drew the y equals x mirror line, notice again that the function I just graphed is perpendicular to this mirror. Therefore, if you flipped it over that mirror, reflected it, it would be landing on top of itself, which means it is self-inverse. Okay, so now let's move on with this algebraic definition of self-inverses, this one here. And let's see if we can do something here. So your job is to show that this function is a self-inverse. I'll help you with A here, okay, just so you can see how we're going to do this. We have this function, and we're going to do this. We're going to put the function into itself. We're going to compose it with itself, and we're going to see if the result is x, because that will tell us it's self-inverse. So here we go. I'm putting the function into itself and trying to show it's x. So here's 3 minus x, but into this x, I'm putting in an input of the same function. So notice that x has been turned into 3 minus x. Simplify this, 3 minus 3, and then that negative makes this positive here, and we have x equals x. We have shown through a proof format, right, that one side of the equation becomes the other side, x equals x. It must be self-inverse. All right, try that with b and c. Do you get the same result? Okay, I hope you tried, and we can see, yes, in b, when you put this function into itself, so that x is replaced by this function right here, simplify that, you get x equals x. And the same in c. When you put this function as an input right here for this x, we get that. Simplify that, we get x equals x. So if we can get to that point where you put a function into itself and we get a result of x, we know it's self-inverse. But now take this a little further. Based on these three you've looked at, can you write a generalization, or can you see a pattern here? They were all self-inverses. And what is true about all three of these? What can you do? What can you write to describe this pattern that you see here? Okay, so the generalization we can make, or conclusion we can make from this, is that when you have a function that takes on this form, n minus x, because notice all of these ended with minus x, minus x, minus x, and n, it was any number in front. Look, 3, -2, half, and n is basically any real number, this means here, okay? So if you have any real number in front and then minus x, it will be a self-inverse. And that goes back to the graph we saw a moment ago, right? Because here we have minus x as well, right? Any function that you graph like this linear function, minus x, is going to be perpendicular to this y equals x line of symmetry. So anytime you write that, it's going to have this slope exactly perpendicular, therefore it will be a self-inverse. So the three that we saw here are basically other versions of this red line, except imagine this red line moving up and down along this green line. So you could plot all these infinite red lines that way. And those are all self-inverses. That's what we discovered here. Okay, let's take this to the next level. This gets a little tougher. We're going to show that this function is a self-inverse function. So let me show you this one first, because for a lot of students, this is a little tricky. There's a lot of algebra here. Okay, we know it's a self-inverse if we put the function into itself and get x. So we're going to put into this function, we're going to put itself. So this x and this x will both be replaced by this function itself, all right? So notice I've rewritten this, but instead of this x and x, I have the function here replacing this x, and this whole function again replacing the x down here. Now this is where the algebra kicks in, right? We want to simplify this and show that it equals x. So on the bottom, if I'm going to combine these two things, I need this 1 to be changed into a fraction with the same denominator. We can only combine these if they have the same denominator. So notice this -1 became this. I multiplied this by x minus 1 over x minus 1, because that will give me the same denominator we can see here. Now we can combine these. So you can simply subtract the tops and write them over a single fraction with that denominator. And that's what we have here. Okay, so I did x minus x and x minus -1, which became +1 here. Combine those into one fraction with this denominator. Okay, now when you have, okay, so take it a step further. These simplify here and then becomes 1 because those x's cancel. Now you can have, when you have division of fractions, you can turn it to multiplication with the reciprocal, right? So this, instead of divided by this, it'll be this times this, but the reciprocal of this right here. And there you can notice right away that this x minus 1, this x minus 1 will cancel. You'll be left with x over 1, which is just x. We have shown that when you put the function into itself, you get the result of x. And since that equals x, we know it is a self-inverse by definition. Okay, so yes, tricky algebra. I'm going to show you another way now, because a lot of students, rather than doing this, they prefer to do this another way, which they find easier, okay, than all this algebra. This is the proper proof, though, because remember when we're doing show, we're trying to show a proof, and we're trying to show that one side of the equation becomes the other. That's a proper proof. But if you want to avoid doing that proper proof, there's another way to kind of reveal that this is a self-inverse. So here's how we're going to do it. Rather than doing f of x into itself, we're just going to take this function and we're going to find its inverse. And if its inverse is the same as the original function, we know it's self-inverse, right? So here's the function written with y here. I'm going to find the inverse by swapping the x and y values. So notice this y became x, and both of these x's became y. Now this is the part where this is going to be a little tricky algebraically, but let's take a look. So now I'm going to multiply this side by y minus 1. I get this here. I'm going to multiply this through here. Gives me xy, and x times this is negative x. Now, since we're trying to solve for y, I'm going to move that y to that side and move this x to this side. I'm going to put all the y things on one side. That's what I have here. So that y went over there and that x went over here. Now, since I have all the y's on one side, I can actually factor y out of both of these terms here. So I factor out a y. Okay, when I take a y out of here, I have x, and when I remove a y from here, I have negative 1. If you multiplied this, you would get back to here. That's factoring. All right, now I can solve for y just by dividing by x minus 1. And we have x over x minus 1. That is our inverse. Okay, so again, most students find this process easier. I found the inverse of this original, and notice the inverse is identical to the original. So we've basically shown it's a self-inverse. The inverse is the same thing. So that's the definition of self-inverse. It's not the algebraic approach, but it is a good enough way to show that these are self-inverses. Okay, so f of x equals the inverse. We're done. Great. Now, let's see if you can do that right here. So this is going to be tough. You're going to pause the video here, you're going to grab your notebook, and you're going to give this a good try. Try it both ways. Challenge yourself. Try it the way where we put this function into itself. In other words, the x here and here will be replaced by the whole function again, and then I'll do all the algebra. And try the simpler way as well, where you just simply find the inverse of this and then reveal that it's actually the same as what you began with. So try both ways. You can do it. Okay, here's the algebraic true proof approach. Notice the function, this whole function has been composed with itself. So this x and this x have been replaced by the whole function. And then all the algebra begins, right? You have plus 1 here. So they're being gentle on you since they have a plus 1. Okay, let's take a look at this some more here. Where was I at? Okay, yeah, they were kind with this function here. They had a 1 here because a 1 is very easy to convert into a fraction here to have a common denominator of 5x plus 1. Okay, combine those, becomes the negative 9 here when those are added. And another thing you should know when you're simplifying fractions like this, where you have a fraction on top of a fraction, if they have the same denominator as these two have, you can simply cancel that from both, and you're left with just what's on top divided by what's on top here. So those 5x plus 1 can cancel. And on the top here, all that reduces to negative x, and simplify x equals x. So if you did that successfully, that's great, because I'm not sure what kind of history you have with rational functions like this, or rational expressions. It's not easy the first time you see it. And then the easier approach, like I said, is simply find the inverse of this. And here is the inverse. I've swapped the x and y values. Take that, multiply by 5y plus 1 over here to get this. Okay, isolate the y's on one side, so that y goes there, that x goes there. Factor out the y here, and divide by 5x plus 1. And we have this as our inverse. And you notice that inverse is identical to the original. Therefore, this must be a self-inverse, because the inverse is the same as the original. Okay, 2 approaches. This is the more appropriate one for proving. This one's okay. And just basically great practice with some algebra here for you. Let's try a few more. This is another idea here. It's a little different. We're looking for the value of k such that this function is a self-inverse. So notice we're given a function. We're told that it's self-inverse, but we have an unknown value here. We're going to have to find out what value can go in here so that this will be a self-inverse. We're going to try this first by finding the inverse. So kind of again like the easier approach, the one where we take this function, find its inverse, and then maybe that will help us. So let's try. To find the inverse of that, okay, there's the function. I rewrote with y here. Now I'm going to swap the x and y values. So write this as x and these two as y, like this. So this is now the inverse. However, we want to rearrange. So it's a function y in terms of x. Okay, so multiply by y plus k over here. Multiply through, and we get xy plus kx. And now we want to isolate the y on one side. So I'm going to take this 3y, put it over here, and this kx over here. I get this. Now that I have y's on one side of the equation, I can factor out y like this. And now divide by x minus 3 and put it over there. So now that is our inverse. Now I want you to, I want you to consider the inverse and look at it compared to the original. And we were told this is self-inverse. That means that this one, the original, and the inverse must be identical. When you look at them, are they identical? Well, I can see identical pieces. There's a -5 here, -5 here. I see something x here and something x here. On the bottom, I see that x. So they are identical. I just happen to have this k here, but I also have a k here. So look, it says x plus k, and this has to be x plus k here also. So that tells us that k must be -3, because that k here is a -3 here. So k must be -3. Now let's check if it works with the other one here. If I just figured out k must be -3, so I put -3 in here, that becomes +3. Oh, it works. So k must be -3. So kind of just by comparing the two, you can decipher that k must be -3. Again, that's the simpler approach, but if we took the more kind of proper algebraic approach, we're going to try now using f of x equals x, right? The definition of a self-inverse. When you put one function into itself, you get x. So let's put this into itself. And here's the work for that, right? Again, we begin with this, and for every time we have x, we put an input of this whole function itself. So you can see there and there. And now the algebra begins, right? Take that further. This 3 here multiplied through here to become this. Great. Now we want to combine these fractions and these fractions, all right? So you're going to have to do the making a common denominator here and here. So over here, you need x plus k to be in the denominator here. So multiply top and bottom by x plus k. And notice here, there's the x plus k. And now you can combine those fractions. On the bottom, we also need an x plus k to be in the denominator of this one here. So we multiply top and bottom right here by x plus k. Now you can combine. So you just combine along the top and write it over the common denominator. So here's what we get there. The first one on top here, we combine those to get this over x plus k. And on the bottom, when you add those numerators and keep the denominator, you get this. Now, I told you last time, if you have a common denominator here, x plus k, you can cancel that. So you're left with this fraction. Now this, let's see what's going on here. Ooh, interesting. So this is not, it's strange that they moved away from a proper proof, right? But this doesn't show you that has to be a proof. It doesn't say show that, so that's not proof. We're just trying to find the value of k. So we don't need to keep the two sides of the equation separate. We can actually multiply this on that side to get this. And then there's some factoring that takes place, and you get to here. Now this is quite complex. You might want to take a moment and just pause and see what's going on, because this is not easy, but basically we're factoring something out of different parts here. I think they grouped the 3x squared and the kx squared, and then they pulled out an x squared from there, and then they grouped the -5x and this one here, and they pulled out an x from there. And when you do that, it says since there is no x squared on the left-hand side, we know that it can simplify to this. 3 plus k must be 0 because there's no x squared, so this must be 0. Yeah, when you do that, you get k equals -3. Same result we did before. Again, much more complex. I would much more recommend to use this approach. So with that, here's one more for you to try, and let's see if you can do it. Here's the complicated way. All right, I'll just reveal that for you here. Again, you can challenge yourself to take a look at that and figure it out. But try the simpler way. Find the inverse of this, and therefore decipher what value must m be in order for this to be a self-inverse. So I'm taking the inverse, multiplying by that, moving the y's to one side right here, factoring, dividing. Hopefully you got here. And now comparing this to the original, you can definitely decipher that m must be -2. Great job. That was a very big algebraic video. Nice work keeping up with this, and we'll see you soon.